Hello and welcome. I'm going to go through the answers to the exam questions on lenses that you've completed. This is answer 1. Lenses are the most common applications of the refraction of light. They are found in eyes, glasses, magnifying glasses and more complex instruments such as microscopes and telescopes. There are two types of lenses, convex and concave. Concave lenses always produce virtual images, but convex lenses produce virtual images only when the object is inside the focus. And the first part of the question asks, what type of image is produced when the object is outside the focus in a convex lens? And how does this type of image differ from a virtual image? So the question indeed is suggesting a certain answer, and also the text above here. So let's just look at this piece of text again. It talks about convex and concave lenses. Firstly, concave lenses always produce virtual images. So let's remind ourselves the concave lens is the one that is thinner in the center, it caves in. But convex lenses, which were asked about in this question, produce virtual images only when the object is inside the focus. And we are asking the question, what type of image do we get outside the focus? Okay, and convex lenses are those that are thicker in the center. So they produce virtual images only when inside the focus, so that leads me to believe that the answer should be the opposite to a virtual image, which is a real image. Now, if you are unsure, what I would do, and what I would do probably anyway, is to draw a quick ray diagram. So it's just a sketch to give an indication of the nature of an image. So we have our horizontal line, the optical axis. We'll draw a lens in the center. Let's mark a focal length and twice that, and the same on the other side. And they should be approximately equal. Of course, you'd have a ruler at your disposal to do that. Now let's place the object far away from the lens, most definitely outside the focus. And a quick ray diagram means that the rays of light go in parallel, out through F, in through the optical center, straight on through. And if you want a third one to confirm, in through F, out parallel. Oops. Alright, so the three rays will coincide over here someplace, and you can see your image there to describe it. The three rays do meet in real space, so it is a real image. It is inverted, and this one is diminished. So you can always sketch a ray diagram to confirm your answer. We're asked, how does this type of image differ from a virtual image? Well, firstly, it can be formed on a screen. And you saw this in the experiment that you did. So real images can be formed on a screen, virtual images cannot. Okay, now let's look at the marking scheme for that part of the question, and let's see how I did. There are 6 marks. Okay, so for the first part, what type of image, there are 3 marks going for it, and the answer was a real image. So yeah, we got that. And how does the type of image differ from a virtual image? That's for another 3 marks. A real image can be captured on a screen, a virtual image cannot. So we got that. Rays pass through the point where the image is formed in a real image. They do not in a virtual image. That's an alternative answer. So if you wrote that, you'd also get 3 marks. So 6 out of 6. Next part, draw a ray diagram to show how a virtual image is produced in a concave lens. Okay, so firstly let's make sure we get our thoughts correct. And it is a concave lens. So what does a concave look like? It's the one that goes in, caves in at the middle. It's thinner in the center, and we expect to get a virtual image. Now, if you're doing this in your exam, you will most definitely be using a ruler, so bear that in mind. So let's draw horizontal line firstly. That's our optical axis. Let's draw a perpendicular line here. This will be the center of my lens, and that's where the change in direction will take place. The lens will be thicker at the sides and go in at the center. Okay, now let's mark some focal points, so equal on both sides, and let's also mark twice that on both sides. Now, if you recall from your lessons, there is only one diagram or one outcome for concave lens. No matter where you put your object, we should get a virtual image. So I'm going to place it out here though, so we have lots of space to work with. Now, and let's track some rays of light from the tips of the arrow. Right, so the rules as always are in parallel, out through F. Now the difference with a concave lens is that we use the focal point on the alternative side of the lens, so on the wrong side of the lens if you want to take it that way. So this is the F we're going to use, and of course this is not happening in reality, so we use a dashed line. In reality the ray of light gets diverged and goes off in this direction. Okay, and the other one we can use, it's the easiest, is to go in through the center of the lens straight on through. Sorry, now you'll have a ruler, of course, it will be better. Okay, and where those two lines intersect, that is where our object or our image will be. Okay, and you'll see it's going to be virtual, so very much smaller, diminished, and it's upright. Virtual, diminished, and upright. Okay, I'm just going to label my diagram fully so the examiner knows that I know what's what, and that's my image. Now let's check the marks for that. Oh, we have another part to that question. Why is a concave lens not suitable for use as a magnifying glass? So even that word there, magnifying, means to make it bigger. We can say that the image, as we saw above, is always, and now you can use the word smaller, or I'm going to stick with our science word that we've been using, diminished. So there were 9 marks going for this part of the question for the diagram, and they're given out in 3 threes. So the first 3, did I draw 2 rays from the object towards the lens? Yes, I did. Did I show 2 rays diverging after passing through the lens? Yes, I did. And did I get an upright, diminished, virtual image on the same side as the object? Yes, I did. So 9 out of 9. And why was the concave lens not suitable to magnify? The image is always diminished in a concave lens. So yes, another 4 marks for me. Light is focused onto the retina in an eye by a combination of a cornea and a lens. The distance from the lens to the retina is approximately 1.8 centimeters, and part 4 of our question asks me to draw a diagram of the structure of the eye. and there are 9 marks going for it. Alright, so we'll have to have studied the structure of the eye and the main parts. So let's draw an eye. Firstly, you have the main kind of sphere shape of the eye, and then towards the front of the eye you have a raised curved area like so. Okay, so the raised curved area has a toughened layer on it, and that is called the cornea. So you're drawing and labeling cornea. Behind that then you have the colored part of the eye, which in this sectional view you just see it from the side, and that there is our iris, and the opening in the center of the iris is known as our pupil. Okay, behind the pupil then, that's where we have our lens. Okay, and we discussed the lens of the human eye, special in that you can change its focal length, or rather the muscles on either side can do it by stretching it or squeezing it to making it thicker. And these are special muscles, they're called ciliary. I think there's an eye there, ciliary muscles. Okay, now there's loads of other parts which you'll learn if you're doing biology, but the next most important for physics is the light sensitive layer made up of photosensitive cells at the back of the eye, and there's a gap there at the very back. Alright, and this is known as the retina. Okay, and it's full of nerves as well, which come together and they leave the eye, making their way towards the brain via the optic nerve. And then the brain forms a picture. Now that's enough, I believe, for physics. For biology you probably need far more detail. So this is enough to track the light. Okay, 9 marks. Diagram must show any 3 of the following. So any 3. And you get 3 times 3 marks to make up your 9. So we included the cornea and the lens. Yes. We included the retina. We include the ciliary muscles that adjust the lens, and we included the iris or the pupil. Okay, that means here if you included one of those 2 you'd get 3 marks, and we have more than enough to get 9. So part 5, how does the eye focus on objects at different distances? Well, we've already kind of discussed it, but what will we write? So very simply, the muscles in the eye, they're called ciliary muscles. We said they change the thickness of the lens. Now there are 6 marks going for this, so I'm guessing it's 3 plus 3. They usually come in bundles of 3, and so for that reason I think we need another piece of information. So we said that the thickness of the lens changes, and this then is changing the focal length. So I think we should mention focal length of the lens. Okay. Part 6. Calculate the focal length of the lens cornea combination, so they work together, if a person views an object a distance of 15 centimeters from the eye. So for this also we need a piece of information that was in the question at the beginning. If you look back through your question sheet, it was mentioned that the distance from the lens to the retina was 1.8 centimeters. We're going to need that. Next, I'm going to do a quick sketch so that I understand the scenario, and in the center someplace I'm going to have the lens of my eye, 1.8 centimeters. Behind that I'll represent the retina, so this is where the image will be, and then not to scale, a distance in front of the lens of 15 centimeters will be my object. Okay, so the retina refers to where the image is. So this information gives me, so 15 centimeter is the distance of the object to the lens, that is U. 1.8 centimeter is the distance from the lens to the image, that will be V, and we're asked to find out what F is. So this is a job for the lens formula. We've practiced using this and it's in your formula and tables books. 1 over F equals 1 over U plus 1 over V. So always write down the formula. You'll see in the marking scheme why. Next, put in the information that you do have. So we don't have F, we do have U, it's 15, and we do have V, it's 1.8. Now, at this stage, you can use your fraction button on your scientific calculators and add 1/15 to 1 over 1.8, and it gives me 28 over 45. Okay, you're free also to do the divisions, 1 divided by 15, and convert to decimals before you add them, your choice. Now, inverting both of these fractions will give me F over 1, which is just F, equals 45 over 28. And dividing 45 by 28, I'm going to get, let's see, 45 divided by 28, I'm going to get 1.6. And all of the values previously were in centimeters, so this will also be centimeters. It's telling me the focal length of the eye lens at that point is 1.6 centimeters. Let's check the answers. So the first one, how does the eye focus the object at different distances? Yes, 2 by 3 centimeter, or 3 marks are given out. So you have to mention the thickness of the lens is changing. That's 3, and refer to the focal length changing as a result. That's another 3. Calculate the focal length of the lens cornea combination if a person views an object at 15 centimeters. So here you see that you get 3 marks for the formula, so you should always make a habit of writing down the formula. Putting the correct values in the correct places in your formula gets you another 3 marks. So now you're at 6 out of 10, and fully calculating will bring you to another 4 marks, which makes 10 out of 10. So how did you do? In total for that question there were 44 marks. So count your marks that you'd have given yourself and put it out of 44, that makes a fraction, multiplied by 100, and that will give you your percentage.